on the planning, there are 3 titles for the 3 talks, and I will take the liberty to switch a bit, but to change a bit my mind, because, well, when I gave the titles, I looked at the program of the conference, and I said, oof, all these guys will learn in 2 weeks what I learned in 10 years, so I should go fast, and then finally decided to go a bit slower. So I will present some of the arithmetical properties of dynamical systems defined by polynomials. And there are major questions in that subject, which is this is a large subject because, as we will see, it covers facts from abelian varieties or elliptic curves. And there are a large amount of conjectures, but there are also some theorems, and in particular, an equidistribution theorem, which I will discuss in the second lecture, maybe in the third one. So I have to understand how it works. Okay, so first I will describe the theory of heights that one can play with when one has a dynamical system. So the dynamical systems I'm interested in come from algebraic geometry. So the simplest case is just the projective line over some field and a rational function, f, defining a map from P1 to P1. And more generally, I could study any closed subvariety x in Pn and a map f from x to x, which is defined by homogeneous polynomials of the same degree, d. So I don't know if it's necessary to recall, but to define f from Pn to Pn, I can take polynomials P0, P0, Pn of same degree. D, and then there is a map which maps the point of homogeneous coordinates x0, xn to the point of homogeneous coordinates P0 of x, Pn of x. And of course, this is only defined outside of the locus where the polynomials P0, Pn simultaneously vanish. And if I assume that there are no common zeros on x, then, so this is a rational map, and if the P0, Pn has no common zero on x, then this may define a map from x to x. So basic examples are elliptic curves with a map of multiplication by 2, by some integer k, well, say greater than 2. There is a very interesting map, self-map of P1, which is induced by elliptic curves. So if you look at the multiplication by k map on an elliptic curve, you can see that the x coordinates of the image depend only on the x coordinate of the point. So there is a map which is called a lattice map because it had been studied by lattice in the 19th century. So fk of x of p is x of kp. And we will mostly see rational varieties like P1 or elliptic curves or abelian varieties, because if you look at the projective curve of genus G greater than 2, then the Riemann-Hurwitz formula allows you to prove that the only endomorphisms are automorphisms and that there are only finite numbers of them. So the theory is not very interesting from the point of view of dynamical systems. You have nothing. So the general setup will be that of a polarized dynamical system. So I take a projective variety x, an ample line bundle L on x, and a map f from x to x, such that the inverse image of the line bundle L is isomorphic to some power L to the g for some integer g, which I assume to be greater than 2, because I want to avoid automorphisms. So the degree of f as a finite map is g to the power of dimension of x. And this definition might look more general than the previous one, where I looked at a rational map from Pn to Pn. But in fact, it's not more general at all, because a very nice theorem of Akrodin shows that if one considers any polarized dynamical system like that, there is some integer n, and an embedding of the variety x in a projective space, such that, well, given not necessarily by the line model L, but by some power of it, L to the n, and a map f on the projective space. So, it is really a map from P to P, not only a rational map. So it is given by homogeneous polynomials of degree d without common zeros, like that. And this map commutes, well, this dynamical system f on the projective space commutes with the dynamical system on x. So it means that f of phi of x is phi of f of x. So in some sense, any polarized dynamical system is just a stable subvariety of some endomorphisms of degree d on some projective space. Of course, if I give you any endomorphism of some projective space and I ask you how to find the stable subvarieties, then the answer will be difficult to find. So it's quite interesting to know, to study them in general. So the examples are, well, some examples are follows. So abelian varieties with morphism multiplication by an integer k greater than 2. Remember, maybe, I don't know if we heard of it, but there is a theorem in the theory of abelian varieties called the cube theorem, which tells you that if the line model L is symmetric, which means that if I take the inverse image of the line model L by the multiplication by -1, then I get L again. Then f star of L is isomorphic to L to the power k to the squared. And so k to the squared is greater than 2 if k is greater than 2. So the projective space gives many examples. Other examples very close to projective space are toric varieties. So varieties are compactifications of a torus. So a torus is something like C star to some power, let's say D, no N. And I consider compactifications of the torus, so X is the projective varieties, so that the multiplication map on T, which is map from T cross T to T, extends to a map from T cross X to X. So these are very interesting varieties that can be described by combinatorics. And they can give you many choices of dynamical systems. And for that, just look at the multiplication by k map on the torus, x to xk, and one proves that this map extends to a self-map of the toric variety, which has the required properties. So f upper star L is L to the power k. And of course, one can consider products or quotients of those examples. For example, the lattice map is a quotient of the multiplication by k map on the elliptic curve. And I'll give you a theorem, which incorporates results of Beauville, Fakrodin, and Zhang. So if XFL is a polarized dynamical system over the complex numbers, I assume that X is smooth. And so f upper star L is L to the D for some D greater than 2. Then the first result is the Kodaira dimension of X is non-positive, less or equal to 0. So this means that there are no well, there are essentially no covariant tensors on the contravariant tensors on the variety. And if the first Chern class of X is 0, then X is a quotient of an abelian variety. So this means that there is, I should not erase that one. So if A is an abelian variety, and you look at the multiplication by K map on A, and then your dynamical system is just a quotient, meaning that there is a map from a finite map pi from A to X. In fact, X is a quotient of A by a finite group. And this diagram commutes. And in some sense, the dynamical properties of F are very close to that of A. So if one knows what happens for abelian varieties, then we might be OK. And Jean proved that if the first Chern class of X is not 0, then X is uniworld. So for surfaces, one has a quite precise classification, not of dynamical systems, but of surfaces admitting a dynamical system. So this classification is essentially due to Nakayama. It's quite recent. And the only examples are abelian surfaces, where the map can only be multiplication by some integer. Hyperelliptic surfaces which admit an étale cover by the product of two elliptic curves, so it's still it's a quotient of some abelian surface. You have toric surfaces and ruled surfaces over unelliptic curves. So these examples are very interesting because if one take a rank 2 vector bundle on an elliptic curve, E. So you have the P of M, the projective vector bundle, which is a family of projective lines parameterized by the elliptic curve. And there are two cases where one can have dynamical systems on such a variety. And one which I would like to discuss is a case where M is a direct sum of the trivial line bundle and a line bundle L, which is a torsion. So it means that L to the power n is equal to OE. So then in X, we can take in X we have two sections. One which I could write 0 and the other which I could denote as S infinity. So. And if I remove the image of these sections, what I get here is something which is an algebraic group, in fact. It is an extension of the elliptic of E by the torus, by the multiplicative group. So J is isomorphic to an extension by the multiplicative group. And so this is a simple example of a semi-abelian variety. And semi-abelian variety fit also in the theory of dynamical systems, but only when they fit. They don't fit really within the framework of polarized dynamical systems, but those who correspond to a line model which is torsion do fit in the theory. So, and the last example which I want to state is, in fact, a non-example. That is that if you take a smooth hypersurface of dimension greater than 1 and of degree at least 3 in some projective space, then it does not admit any endomorphism of degree greater than 1. So this shows you that such varieties won't admit an interesting dynamical system. In the 90s and till now, there have been other examples of dynamical systems which are related to polarized dynamical systems but don't fit in the picture, and I would like to mention them, which are automorphisms, in fact, of a complex or smooth projective surface with positive entropy. So I do not want to define what entropy is, but it means that for people of ergodic theory, the fact that the entropy is positive means that the dynamic is interesting. And in that case, one can find within the Picard group a plane, I mean a two-dimensional subspace, on which is stable under the action of the dynamic system, dynamical system, and such that this action on this plane is diagonalizable. Okay, so it has two eigenvalues. The one is the exponential of the entropy, lambda, which is greater than 1 because the entropy is positive. And the other is the inverse of the entropy, so it's smaller than 1. And these two eigenvectors are not really line models. They are only line models with real coefficients. But it is possible to develop the theory so that to incorporate such objects. And this gives you a theory of canonical heights, as I will describe later. And the example of Silverman is just a K3 surface in P2 cross P2. So you take the intersection of a 1-1 hypersurface. So it's an equation which has degree 1 in the first set of variables and degree 1 in the second set of variable. And a 2-2 hypersurface, so degree 2 in the first set and still 2 in the second one. And taking this 2-2 hypersurface gives you a possibility to gives you an involution, because if you have a solution of one quadratic equation, then you can switch to the other one. So you have two involutions, sigma 2 and sigma 1, and if you take the composition of them, then you'll get an automorphism, because the composition of two involutions is an automorphism, and the entropy is equal to it's the logarithm of 7 plus 4 square root of 3, so it's positive. So this is an example of Silverman, and there are some others. So you have probably heard of the near-rounded height on elliptic curves, Henry? Yeah? So for the case of dynamical systems, there is a generalization. So I take so for elliptic curves, remember that you have I'll say if we have k upper star L equals to L to the power k squared, and the near-rounded height has the virtue that the height of k times a point is equal to k squared times the height of the point. And for dynamical systems, it's possible to define a similar height, which I will call the canonical height. So I first consider any height function relative to the fixed line model L. So I remember that this means that if phi is an embedding of x in a projective space such that phi upper star of O of 1 is L to the power n, so the power Ln is a semilinear series at the hyperplane section of the embedding phi, then h of x is equal to the veil height of the image of phi of x divided by n up to a bounded amount. And the machinery of height tells you that the difference of the height of f of x and d times the height of x is bounded when x varies along all algebraic points of the variety x. And, well, the Tate's trick allows you to prove that there is a unique height function, which I call h with a hat, so that it is to recall that it is canonical, which is relative to the line model L, such that the canonical height of f of x is precisely equal to d times the height of x. So the proof of this theorem is very easy. It's just, I don't know, well, should give the proof at some point. So it's just an application of the fixed point theorem. For instance, you define hn of x equals to 1. You take the nth iterate of x, you look at it as you compute its height, and you divide by d to the power n, and you can prove that hn of x converges to something which you call h hat of x when as n goes to infinity. So I want to discuss some consequences of this canonical height concerning periodic points on dynamical systems. So the major virtue of height is that is given by North-Scott theorem, with what is called North-Scott theorem nowadays, meaning that there are only finitely many points of bounded height on bounded degree. So for any integer d and b, there are only finitely many points x, such that the field of definition of x has degree less than d, and the height of x is less than b. And as a consequence, one recovers North-Scott's original motivation. In fact, North-Scott's theorem is precisely what is within the red box. So first of all, the canonical height of any point is non-negative, and the points whose height is 0 are precisely the periodic points. So the proof is easy. So look at some point, some algebraic point, x. First of all, you can take a finite extension, E of f, such that the point x belongs to x of a. So we will first assume that the canonical height of x is non-positive. And we will prove that, in fact, the height is 0 and that the point is periodic, pre-periodic. So first of all, the height of the nth iterate, the canonical height of the nth iterate, is equal to d to the n times the canonical height of x. So this is non-positive. But all these points fn of x have bounded degree, at most the degree of E over f, and bounded height, because the canonical height is less than 0. And North-Scott's theorem, that one, implies that the sequence, well, the set x, f of x, f square of x, and so on, the set of iterates, is finite. So this means that there are two integers n and p with p positive, such that fn of x equals n plus p of x. So fn of x is pre-periodic and x is pre-periodic. Pre-periodic means that some iterate is periodic. Pre-periodic means that some iterate is periodic. Okay? F is a number field for the theory of height. It was up. Well, over function fields, the theory is a bit more complicated because North-Scott's theorem, North-Scott's finiteness theorem is not true over function fields in general. So, well, some remarks. The first one is that considering the set of periodic points is considering a large set of points, because the set of periodic points is Zariski dense. The sets of periodic points is Zariski dense. So I know of two proofs of this assertion. One is belongs to ergodic theory, and it is essentially due to Briand and Duval. And because it shows you that the closure of the set of periodic points is a support of a measure of which, for which the Zariski subsets have zero measure. So this means that the Zariski closure of periodic points, this implies that the Zariski closure of periodic points will be equal to the whole variety. And there is a proof, a completely arithmetic proof, which is due to Fakhruddin and Poonen. Well, it appears in a paper by Fakhruddin, and then the main lemma is due to Poonen, so it's hard to tell who proves that. But nevertheless, the hard part of the proof is due to Hrushevsky. It's a theorem in the theory of in the model theory of fields with, well, fields, not fields with difference, but fields together with automorphisms. And so this gives you an arithmetic proof of the fact that the periodic points are Zariski dense. And if you only want to know that the set of pre-periodic points is Zariski dense, then it's easy to write down a proof, because take V, the Zariski closure of the set of pre-periodic points. So the image of a pre-periodic point is a pre-periodic point, so f of V is equals to V. Well, no. So f minus 1 of V is equals to V, and the inverse image by f of a pre-periodic point is still a pre-periodic point, so f of V is equal to V. And now this equality implies that the degree of the restriction of the map F to V is equal to the degree of F. And if you look at the degree of F restricted to V is d to the power dimension of V, the degree of F is d to the power dimension of X, so you have the equalities. Sorry? D, exactly, D is everywhere, D is such that f above star of L is isomorphic to LD. So D is k squared if f is a multiplication by k on an elliptic curve. Hop. So I want to give you examples of pre-periodic points on periodic points. So on abelian varieties, if the most interesting morphism is multiplication by some integer k, and then a point is pre-periodic for this map if and only if it is a torsion point. And in that case, the canonical height that one recovers is precisely the neuronted height. For the projective line, if you look at the map x to xk, then the pre-periodic points are exactly 0 and infinity, and the roots of unity in the affine line. And the canonical height is exactly the veil height, because it's a standard thing that is proved in the height theory, that the height has this canonical property. And in that case, Northcott theorem about the fact that points of height zero, that points of height zero are pre-periodic point is a classical old result of Kronecker points which are algebraic integers, and all of which conjugates have absolute value at most 1 are roots of unity, except 0. So this finishes the first part of the talk, which was the description of the height machine that one can play with when one has dynamical systems. And the second part of the talk is devoted to conjectures. So the first one, so first, well, I've put names on almost all of the conjectures. So these names are not an accurate. You should not believe that those guys did conjecture those statements. But all of these statements are inspired by conjectures of the named people. So the first one I named is lemma. So if you consider a dynamical system over a number field, and you could ask if the height of any point, the canonical height of any point, is bounded below by something positive if the point is not pre-periodic. And the best lower bound than one can expect is some constant divided by the degree of the point. And it is the best conjecture that one can make, because if one takes a pre-image of the point x, then the degree of the field generated by the pre-image will be at most d times the degree of the field generated by x, and the height will be divided by d. So one cannot expect anything stronger, and lemma expected that result in the case of veil height, so in the classical case of the projective line. And what is known about this conjecture in general? Almost nothing. If you look at the projective line, so and the classical veil height, then it is easy to see that if the height of points which are non-units or non-totally real have the height bounded below by such an expression, constant divided by the degree, but nothing more is known except from, well, the strongest result which is known is Dobrovolsky estimate, which claims that the height of x is at least constant divided by the degree to the power 1 plus epsilon. In fact, Dobrovolsky had something where the epsilon is replaced by log of the degree divided by log of the degree, but well, and with some exponents. So this is enough. And Michel Laurent proved an assertion which is similar to that of Dobrovolsky for elliptic curves, but the one is replaced by 3. And both proofs rely on classical Diophantine approximation. So the second conjecture is due to Morton and Silverman, and I had not enough place to put the picture of Morton, so I apologize to him. So, and this is not Morton-Silverman's conjecture, because Silverman's conjecture is only for the projective space. So consider a dynamical system, a polarized one. So, and then you could ask how many periodic points or pre-periodic points there are over a given number field. You know that they are finitely many because they have canonical height 0, so the Northcote's finiteness theorem tells you that there are finitely many pre-periodic points. But you could ask if there is a bound which depends only on the dimension of the variety, the degree of the embedding of the variety given by the ample line model, the degree of the map, and the degree of the field of definition. So the Fakhruddin's theorem, which I presented earlier, implies that it is sufficient to treat the case of the projective space over the field of rational numbers. And in that case, you get Morton-Silverman's conjecture. But if you look at an abelian variety, then the dimension is what it is. The degree of f, well, for a map f, you could take multiplication by 2, then the degree is, the integer d is just 2. Well, look at a, say, principally polarized abelian variety, then capital D is equal to factorial of dimension. And so if that conjecture is true, then as a consequence, a much more very general statement in the theory of abelian varieties is true, namely that you can bound the number of torsion points only in terms of the field of definition, of the degree of the field of definition, and the dimension of the variety. And that result for specified to abelian varieties is far from being known, except for elliptic curves, where it has been proved by Maser when the field is equal to Q, by Merel in general. So you see that the conjecture is widely open, but there are many interesting results in a similar nature to those results on Merel's theorem, which were known earlier. Namely, if you bound the ramification at some places, then you can say something. So the third conjecture is Manin-Murford's conjecture, also an analog of Manin-Murford's conjecture. So we will consider a polarized dynamical system over, let's say, an algebraically closed field of characteristic 0. I denote by P the set of preperiodic points. And remember that P is the Zariski-dense in the variety X. So now if V is a subvariety of X, I can look at the preperiodic points which lie in V. And the conjecture is that this set of preperiodic points, so P intersected with V, will be Zariski-dense in V if and only if there is a strong geometric reason for that, namely that the variety V is itself preperiodic, meaning that if you look at the iterates, V, f of V, f square of V, etc., then you will fall back to some iterates at some time. So it is easy to see that if you consider a preperiodic subvariety V, so then if you assume that Fn of V is Fn plus P of V, then the preperiodic points in V are Zariski-dense in V, because you have a dynamical system in V, you can, not in V, but you look at the nth iterate of V, so let W be you have the map f to the power P, which goes to W to W. But preperiodic points for Fk are exactly the preperiodic points for F. And so P intersected W is Zariski-dense in W. And from that, you can prove that the set of preperiodic points in V are Zariski-dense in V. So the difficult part of the conjecture is the converse. And it is far from being known. So the case of abelian varieties was conjectured by Manin and Mumford and has been proved by Michel Reynaud in the 70s, beginning of the 70s. So in that case, the theorem you get is that the set, you consider an abelian variety, A, a subvariety, V, and you assume, whoop, there is something missing on the slide. So you assume, write it. So you have an abelian variety. A subvariety V. Assume that the torsion points of A lying in V is Zariski-dense. Then V is of the form P plus B, where B is a subvariety, is a sub-abelian variety, and P is a torsion point. So the case of toric varieties, where the morphism is just the extension of multiplication by k on the torus, is also true, and it has been shown by Michel Laurent. And for general dynamical systems, except almost nothing is known. So there is a a thesis by Mimar in something like 95, who he studied the maps on P1 times P1, which are of the form xy goes to f of x, g of y. So for two rational functions f and g. And the assumption, well, one of the assumptions he proposes is that the Julia sets of f and g are different. So in that case, he can really determine all the stable subvarieties and prove the conjecture. And in fact, the preperiodic subvarieties, the preperiodic curves, are only the trivial one, x times p1 and p1 times y. So there is a strengthening of Manin-Mumford's conjecture where height functions intervene. And the name is Bogomolov. So I still consider a polarized dynamical system over number field F. And I consider the canonical height, h hat. And then if Manin-Mumford's conjecture is true, if V is a subvariety of X, which, I take V as subvariety of X, and V naught the union of all preperiodic subvarieties lying in V. Then outside V naught, in V minus V naught, there will be no preperiodic points, because preperiodic points are subvarieties. So it is natural to ask if the height, the canonical height, is bounded below, outside V naught. Of course, in a preperiodic subvariety, you can divide points. You can take preimages, and then this divides the height at indefinitely. So the height will not be bounded below by something except by 0. But if you exclude all preperiodic subvarieties, then you might hope that the height is bounded below. So in fact, Bogomolov had conjectured this when X is a Jacobian of a curve of genus greater than 2, and V is not a curve, but when V is a curve. In fact, the curve. So this generalization has been proposed by Shou Zhang. And I should say that it is this conjecture, it is a theorem in the case of abelian varieties. It's a theorem proved by Zhang after a breakthrough by Emmanuel Hulmeau, who showed the case conjecture by Bogomolov. And then Zhang generalized the conjecture. And the way to the proof of the Bogomolov conjecture for abelian varieties is a result of equidistribution, which will be the topic of my talk tomorrow. And so equidistribution means that when we look at points, well, it's a sets of points, a finite set of points, they will define a measure. You take the counting measure, the discrete measure supported by those points. You divide by the number of points so that it is a probability measure. And you will look at the behavior of those measures when the number of points grows. And the limit measures that one will obtain are very important in the theory of ergodic, in the theory of dynamical systems. And so I described them first. So I still look at the polarized dynamical system over the complex numbers. G is an integer such that f up of star L is L to the D. And so I describe the canonical probability measure, which is supported by the complex points of the variety. So to define this variety, you just need to take any volume form on the variety. So it's a differential form of maximal degree in the sense of, so the degree is 2 times the dimension of the algebraic variety X. And then what you can do with this form is to pull it back. using the dynamical system, F. So you pull it back n times, and you divide it by n d to the power minus n dimension of x. So that you still have a probability measure at each point. And the basic fact is that when n grows to infinity, these volume forms converge to a probability measure, mu f, on x of c. So this probability measure satisfies two functional equations. The first one is easy to understand. It says that the direct image of this measure by the map f is equals to the measure mu again. And the second assumption is a bit more difficult to understand, because I look at the pre-image of a measure. So this is strictly forbidden by integration theory. There is no pre-image of measures in integration theory. So what happens here, that the map f is not any continuous map. It's something defined by a polynomial. So I can define the pre-image of a measure so I have to integrate some function, phi. And to do that, I just integrate on x the function against some measure mu, the function phi of y. So I integrate the sum of the values of the function phi at all the pre-images of the point. And the fact that f is a polynomial implies that this function is continuous in x. So this makes sense. Well, it should be flat too. It is. No, it does not depend on omega, but it does not mean that it does not depend on omega. But of course, it does. If you take the map x to goes to x squared on the projective line, then you have three measures. You have a cone of measures satisfying these two equations, and the extreme points of this cone are the Dirac mass at 0, the Dirac mass at infinity, and the Haar measure on that measure. So you can take linear combinations of them. So you begin with something which is a smooth volume form, and then you pull it back. So mu may have singularities and has singularities at very bad singularities. So so if you take an abelian variety, then the measure you get is the Haar measure on the abelian variety. If you take a toric variety, say if you take P1 and the map x goes to x squared, then you get the map, the integration map on the circle, and more generally, the integration map on the maximal compact subgroup of the torus. So this measure is very important in the theory of complex dynamical systems. So it is a unique measure of minimal entropy, so it means that you have something, a characterization of that measure. The first point. The second point, if you look at periodic points, points of order n, and you take the integration map on that set of points, and you divide by the cardinality of this set, then this discrete measure converges to the measure mu f. So this is an equidistribution theorem in the framework of complex dynamical systems. And they go back to Brolin and Lubitsch in the 60s, and Briand, Duval, and Gage. So they are quite recent in the case of general algebra varieties. Moreover, one can show that this measure does not charge Zariski subsets, strict subsets. So this implies that the Zariski closure of the support of this measure is equal to the whole variety. But remember that if you look at P1, then the support of the measure was just the circle. So this is a closed subset, which is far from being equal to the Riemann sphere. So now what means equidistribution in my arithmetical context? So I fix once for all an embedding of the algebraic closure of f in C. Okay? So now if x is any algebraic point, I can define a discrete probability measure, delta of x, on x of C, which will be invariant under the Galois group of C over f, as follows. So I denote by S the degree of the field generated by x. So, and by x1, xs, the set of conjugates. And I simply define the measure delta of x to be the mean of all the Dirac measures, delta xi, so supported as conjugates. So this is a discrete measure. And the equidistribution question is the following. If you take a sequence of points, a sequence of algebraic points, satisfying the following two assumptions, so I will read the second one first. So you assume that the height goes to 0, the height of this point goes to 0, and then you assume that for any strict subvariety V, there are only finitely many integers n, such that xn belongs to V. So I will comment on that later. So then, granting these two assumptions, is it true that the measures delta of xn converge to the canonical measure mu f? So let's look at the example of the projective, the Riemann sphere and the map x go to x squared. Then you can look at the nth root of unity. What you know is that the nth cyclotomic polynomial is irreducible, so the conjugates of some n roots of unity over Q is just all exponential 2 by I k over n for k and I coprime. And it's easy, it's not difficult to show that when n goes to infinity, this set of points converge, equidistribute to the integration measure on the circle. Without the condition that the k and n are coprime, it is easy, it's just a theorem of Riemann sums. Well, then one has to play a bit with this coprimality condition, but it's not serious. So I need to comment the assumption, the first assumption. So if some variety V was containing infinitely many xn, then, and if the conjecture if the conjecture was true, then the limit, some limit value of the measures delta of xn will be supported by V. And we have seen that the support, the Zariski closure of the support of the canonical measure mu f is equal to x. So it's not possible that such a theorem is true if one removes the assumption that no subvariety contains infinitely many points. So in the case of abelian varieties, this theorem has been proved by Spiro, Ilmo, and Zhang. And this is, the main tool for the proof of Bogomolov's conjecture by Ilmo and Zhang. So the proof of Bogomolov's conjecture goes by using twice the equidistribution theorem in two related contexts, and then showing that these two equidistribution theorems are incompatible. And so there is a contradiction somewhere. And the interesting case for people in ergodic theory is the case of the projective line. And there are two kinds of proofs in this case. There is one proof by Autissier, which uses Arakelov theory as was used by Spiro, Ilmo, and Zhang. And the other proof by two groups of people, Becker, Rumley, and Favre, Rivera, Letellier, use potential theory. So I won't give many details on that proof, but remember that potential theory is very closely linked to number theory, since the works of Fekete and Schege in the beginning of the 20th century. So it's not a surprise that potential theory allows people to prove result in number theory. And in fact, the equidistribution conjecture is not a conjecture, it's a theorem now. But it was a conjecture some months ago, so I received a preprint in March by a student of Shou Zhang. And the proof of the general theorem uses Arkelov geometry. And I should mention, I will maybe talk a bit on that on the third talk, that there is a p-adic analog of this equidistribution theory. But this is, well, for these analogs, one has to, it's not sufficient to look at the CP points, the classical points over the algebraic closure of QP, or let's say the completion of the algebraic closure of QP. One really has to look at what happens on Berkovich spaces. And these Berkovich spaces are the place where equidistribution takes place. So in the next and last conjecture is the existence of dense orbits. So consider again a polarized dynamical system of a number field. Does there, how do you say? So, well, the question is there. Does there exist a point P over Q bar whose orbit is Zariski dense in X? So the set of preperiodic points is countable for any integer n. There are only finitely many points of order n. And so with that, you can prove that the set of preperiodic points is incountable. So the existence of non-preperiodic points over Q bar is not totally trivial. It could be possible that over Q bar, all points are preperiodic because there are countably many of those. You see, when Weil, in Lang's file about Shimura-Tanyama Weil answered at some place that it might well be true that all elliptic curves are modular because both sets over Q are modular because both sets are countable. So, so nevertheless, it's easy using the height machine to show that there are non-preperiodic points. Because if all points over Q bar were preperiodic, then the height will be 0. And it's well known that the height is not bounded over Q bar. So at least there are non-preperiodic points. But it might be possible that any point in Q bar lies in a strict subvariety, which will be stable under the dynamics. But also, when the dynamical system is an abelian variety, then the theorem is, well, the question is true, as a positive answer. And over uncountable fields, so say, then the result is also true using recent theorems of Campana and Americ about the structure of such dynamical systems. But the result is totally open, say for a dynamical system on P2, given by 3 polynomials without common zeros. Nothing else. So that's all. Thank you.